In this video, we're going to look at the Module 15 R code, and you might notice my desktop looks a little bit different than it normally does. I'm on my personal computer. Normally I make these in the recording studio. So again, bear with me. It's going to look a little bit different and the audio quality might not be as good as it typically is in this video or in these videos. Alright, so the first step is we always want to start out by having all of our files that we need in a folder on our computer. And so for this video, I'm going to need the Word document with the notes, or PDF would be the version that you have, the Module 15 R notes, as well as our data set. And you'll also want to make sure that you have the code book handy. So to get started, let's go ahead and look at the R code as well as the Word document. So you'll see that I've got RStudio open here, and I've got that R code file. And then also we can look at the Module 15 notes. So these notes are going to look very similar to the Module 12 and the Module 13 notes. And what we're going to do in this video is look at several common hypothesis tests for quantitative data. The first one being the one sample t-test. So one sample t-tests are really useful when you have a question about a population mean and you'd like to compare it to some fixed value. And this could be some historic value that you want to see if your mean is higher than or less than, or some value that makes sense in context. In particular, for this example, we're going to look at the BMI of people living in Kentucky during the year 2018, and we might want to know, on average, is the BMI for all people living in Kentucky during 2018 greater than 25? And to answer this question, what we're going to do is we're going to take our sample data and see if there's enough evidence in that sample data to suggest that this is the case. And so we can use the one sample t-test here. So in order to do this, I'm going to go to my R code. Remember, the very first thing we always need to do is to read in our data set. And in order to do that, we need to set our working directory. So I'm actually going to show you a different way to set your working directory in this video. If you come over here and you click on Files, you have access to all of the files on your computer and you can navigate it like any other file explorer. So what I'm going to do is I'm going to navigate to the folder on my computer where I have these notes, and you'll see that that is right here. And what you can do is if you click on the More button, you'll see there's an option for Set Working Directory, and it will actually go ahead and enter the code for you. And you actually saw this way back at the very beginning of the course, but it's always good to kind of refresh on these things. So our working directory is set, and now we just need to read in our data set. So our data set is read in, and we can see our data set's up here, and if we wanted to, we could view it. Alright, so remember, for any hypothesis test or confidence interval that you perform or you calculate, there are always assumptions that go along with the different methods. So in practice, you always want to make sure that for whatever confidence interval or hypothesis test you're performing, that you're familiar with the assumptions for that particular method, and your first step is to always make sure you haven't violated them. If you have violated them, that tells you probably need to use a different method. And what you'll find is for just about any research question that you have, there are different options of confidence intervals or hypothesis tests that you can use to address those research questions. But a lot of times which ones you choose will be based on some of the characteristics of your data set and whether or not you have violated certain assumptions. So for that one sample t-test, we want to make sure that our sample size satisfies the central limit theorem, and we also want to make sure that we don't have a whole lot of outliers or a real heavy skew to our data. Now, as long as our sample size is large enough, that won't particularly matter, but it's always a good thing to double check. So just like we've done before, we could look at a histogram of BMI. We do see it has a slight right skew, but it's not overly concerning, especially considering that our sample size is massive here. And we can see that if we look at the non-missing values for BMI, we've got over 6,000 observations. So central limit theorem is going to take over. And so even though we have a slight right skew, that's no reason for concern, and we're more than valid to use the one sample t-test. Now we can look at the mean BMI for the sample. Now, one thing to remember here is that the way that the data set codes BMI. So let's look at that variable in our data set. Okay, so here's our data set. So remember that it has 2 implied decimal places. So we do want to be careful whenever we are interpreting these values. So when we see that our sample had a mean of 2,924, that doesn't mean they have a BMI of 2,924. That really means on average, or the average BMI is 29.24 here, because we can't have BMIs in the 2000s. All right, so we're going to perform a t-test. So let's go back to our R document. So remember that we were going to perform a t-test to see if BMI is greater than 25. So keeping in mind that we have those 2 implied decimal places, with the format of our data, that's really asking if it's greater than 2,500. Okay, so you want to make sure that however you ask your question matches with the format of your data set in the actual data file that you get. The other option, if you wanted to compare it to 25, then you would need to convert your column of data so that it was in the correct format. Either way is going to give you the same answer. So looking at the R code, what we've got here is we have read in the BMI variable, and you'll notice we're using the t.test function. We also used this when we made a confidence interval for a single mean, but I'm going to give it some extra information. I've got to give it the value mu. This is the value that mu takes under the null hypothesis. So again, we're just putting that, our question is really about BMI greater than 2,500, but we have to convert this over to the format that the data is in. So that's why we've got 2,500 here. And on the alternative, we have greater, because again, this is a right-tailed test. And most of the times when you work with quantitative data or functions that deal with quantitative data, a lot of times you're going to need to add this argument here, which tells it whenever you do any calculations to remove the missing data. So let's run this. And you'll notice we get some output, and this output again is very similar to the output we got when we looked at the confidence interval for a single mean. So if we go over to our Word document, which we have here, you'll notice that that output has been copied. And so the pieces of information that you want from this output are these pieces right here. Notice we have our test statistic, the 49.971, which is a very large test statistic. Our degrees of freedom here, you'll notice that is the sample size minus 1, and then our p-value. And our p-value here is effectively 0. So what this tells us is at the 5% significance level, because this p-value is less than 0.05, we do have evidence that the mean BMI of people living in Kentucky during the year 2018 is greater than 25. Now, one kind of comment on the conclusions, and all of the conclusions I have presented them this way, where we say at the 5% significance level. And you're going to learn in this module that people are starting to move away from this set significance level, and instead of reporting their conclusions this way, they're just reporting it in terms of what the actual p-value was. And so you'll see that when you move over to the next module. All right, the next question we're going to look at is very similar, but this is a 2-sample t-test for 2 populations means using independent samples. So you'll notice I have skipped over the paired data example. The reason for that being is that for the BRFS data set, we don't have paired data, so it wouldn't make sense to use that particular hypothesis test with this data set. If you do need to run a t-test for paired data, you'll actually use the t.test function just like we did here, but instead of giving it the vector or the data that would be the BMI in this case, you would give it that vector that has the differences, and your null hypothesis, or the value of mu under the null, would be 0. All right, so let's see how to do the 2-sample test. So this time we're going to ask, is the mean BMI for people living in Kentucky with good, better health different than the mean BMI for people living in Kentucky with fair, poor health during the year 2018? And again, you're going to notice that this is pretty much the same question we asked when we looked at the confidence interval for a difference in means, and the output is almost exactly the same. All right, so going to our R code here, you'll notice we're going to start out the same way that we did with the confidence intervals. I'm going to create 2 vectors, one to store the BMI for those that reported having good, better health, and one vector to store the the values of BMI for those people reporting fair poor health. We did this exact same thing earlier when we looked at confidence intervals. Same as before, always got to check my assumptions. So what we've got here is I'm going to look at, what's my sample size in each of the groups. I'm also going to look at those histograms. And so we have this here, and you'll notice that's the exact same, again, output that we saw when we worked with the confidence intervals. Just like when we worked with confidence intervals, we've got to make the decision, are we going to make the assumption of equal or unequal standard deviations? And so that's what this code is doing. Again, the code is pretty much copy and pasted from when we looked at confidence intervals. And so here are the two different ways to perform the test, one assuming equal variances, one not. And again, code is the same from when we worked with confidence intervals. So we could run either of these, and then depending on which one we choose. In the Word document, I chose to go with the assuming equal standard deviations because that was the same choice we made when we looked at the confidence intervals. And so you'll see that output right here. But now, instead of looking at the confidence intervals like we did last time, we're interested in this piece. And again, we have our test statistic, the degrees of freedom, and our p-value. And note that our p-value is very small here, so we are able to conclude that that mean BMI is different between the two groups. All right, next we're going to look at the Anova test. Now the Anova test is something we haven't seen yet. And what the Anova test does is instead of just comparing two groups, it gives us a way to compare more than two groups. So for this particular example, what we're going to do is we're going to look at smokeless tobacco use and see if the mean BMI differs with respect to different levels of tobacco use or smokeless tobacco use. So coming to our R code, the smokeless tobacco variable is the useNow3. So let's go to the code book and look at what that variable looks like. Alright, so here's our variable. So notice there are three levels that we're going to be interested in. There's the everyday, someday, and the not at all. And then of course the don't know, not sure, and refused. Those are the ones that we're going to remove from the analysis, and then we're going to document that those groups were removed. So what you're going to see is this is going to look very similar to what we did before, but now we have three levels that we're interested in. So what I've done is created three different vectors to store the data for each of the different levels of smokeless tobacco use. So I've got those that use everyday BMI, those that use some days BMI, and the not at all groups BMI. So these are my three different groups I'm interested in comparing. And again, by setting up these three different vectors or these three different objects to hold the data for these observations, this is getting me away from having to worry about the not sure and the refused. Just like we did when we looked at the confidence intervals, we want to look at the histograms for each of the groups, and we also want to look at the sample sizes. The Anova by default does assume equal standard deviation between the three groups, so you do want to make sure that there isn't a drastic difference in variability between those three. And so let's look at some ways to check those assumptions. Again, I'm going to look at I need to run this code here. All right, first I'm going to look at the histograms for the three different groups. One of the assumptions that's made in the Anova is normal populations. So here's my first one. I do see a slight right skew, but I'm not terribly concerned by that. Similar for this one. And similar for this one. So even though there's a slight right skew, my sample sizes are so large here that I'm not terribly concerned about that assumption of normality, and the Anova test is fairly robust to that assumption. One way to compare the variance between the three is to look at side-by-side box plots, and so we have that here. So looking across the three box plots, in terms of the spread of the data, there's not very much difference between these three, so I'm not too worried about my assumption about equal standard deviations. Next, we can perform the Anova test. So in order to perform the Anova test in R, what we have to do is we have to take the three vectors that we created up here, which stored the BMI for the three different levels, and we have to make it a new data set. And so that's what this code right here is doing. I'm going to name my new data set BMI.data, And the data.frame function, what it does is it creates a data frame using whatever I give it. So I'm going to define three different things. First, I need to define BMI, and what BMI is going to be comprised of are my three different vectors that I created earlier. Next, I've got to create the smoking level. So this will be the way that I denote whether someone smokes every day, some days, or not at all. And then what I'm going to do is I'm going to have to repeat this over and over again, however many observations are in the every BMI, the some BMI, and the not BMI. And so that's what this times is doing. So let's run this code and then have a look at what the resulting data frame looks like to help us see what this code is doing. So I've created the BMI.data data set. Now what this line of code is going to do is it is just going to look at the first 10 rows. So if we run this, here's the first 10 rows. So what this chunk of code right here does is the first column, these are going to be all the different BMIs. And by placing these in order, what it's done is it's put all of the every BMIs and then all of the some BMIs and then not all of the not BMIs. And then the second column it creates, what it does is next to each of the BMIs, it tells us which of the three levels that value came from. So that's what this times is doing. What this does is it sees how many every BMIs there are, and it repeats the word every that many times. So that way in the left column, when we have all the entries of BMI for this group, it puts its level next to it. So now that we've created the data set this way, what we can do is run the Anova test. To do this, we create an object, and I'm going to call it BMI Anova. And then I'm going to use the AOV function. So the AOV is analysis of variance. What we're looking at is BMI as a function of smokeless tobacco level. So that's what this does. And then I tell it what data set we're using, which is the data set we just created. So we can run this. And we get our output here. So I've copied this output into the Word document, so let's look at it. It's been copied right here. The piece of information you're most interested in is your test statistic and your p-value. And so remember, the results in an Anova test are given in an Anova table. And so highlighted right here are the test statistic, which is the F-test statistic, and our p-value. So notice our p-value here is 0.04, so it is less than that 0.05 cutoff. So if we're going to use that cutoff, our results are significant here, and that tells us that that BMI does differ with respect to those three groups. Now the Anova test only tells us that there is a difference. It doesn't tell us where that difference occurs. So we could do a multiple comparison test. One such test is Tukey's test. And so to perform this test in R is fairly easy. We use this function right here, which is Tukey HSD, and then we just feed it that object that we created from the Anova test. All right, so looking at the output here, what the Tukey's test does is it looks at all of the possible pairs between our three levels. So we could compare those who don't use smokeless tobacco to those that use every day, some days to every day, and then some days to they don't use it at all. These are the only three possible pairwise comparisons that we can make from our three levels of smokeless tobacco. And interestingly enough, if we look here at those p-values, notice that all three of these are not significant. I chose this example because this is fairly atypical. You're not going to see this very often. Most of the time, if you run an Anova and that Anova is significant, at least one of these pairs will also be significant, and that's going to show you where the difference is. Occasionally, and by occasionally really I mean rarely, something like this will happen. You will get the overall F-test or the Anova test is significant, but when you go to make the pairwise comparisons, none of them are. The reason for this is because the Anova test is looking at this overall difference, but on the pairwise level, it ends up that none of them are significant. And we can see that this one right here is very close to being significant. Results like this help add to the argument that when we run hypothesis tests, instead of using this hard and fast cutoff of 0.05 or the significance level, maybe we should just report the p-values for what they are. And again, when you look at our next module, 15.3, I'm going to have you read an article where you actually look at that discussion. And so keep this example in mind while you're reading that discussion and why it might be useful just to report the p-values instead of using these significance levels as cutoffs. All right. Last thing we're going to do is we're going to look at the regression hypothesis. And what you're again going to see is the code is pretty much the exact same code that we ran when we fit the linear regression earlier in the course. So this time we're going to look at the relationship between height as a predictor oops, I just realized there's a typo here. Let me fix that really quick. All right, so we could fit a simple linear regression where we use height to predict weight. And so there's two different hypothesis tests for the for linear regression, for simple linear regression. The first one is, does simple linear regression model with height as a predictor do a good job at explaining the variability of weight? In other words, if we know a person's height, does it do a good job of explaining why weight might vary from person to person? And then further, is there evidence that the slope of the line is non-zero, which again, that helps suggest a linear relationship. So if we go to the code, you'll find that the code is exactly the same code that we saw back in Chapter 9 when we fit the linear regression model. So I'm not going to spend too much time on this code because again, it is exactly the same. So running the code here, we have this piece of code here where we fit the model. And if you'll remember from before, that's where we got the regression line from. In other words, in our scatter plot, that's how we got this line that goes through our scatter plot. But this code does some more for us. So if we look at the output that's given, I'm going to do this in the Word document. Here's all the output. You'll notice there are two different sets of p-values. The first one given at the very bottom, that is our overall f-test. And so that's the one that corresponds with the question, does the simple linear regression model with height as a predictor do a good job of explaining the variability of weight? And you'll notice down here the p-value is very close to 0, so we are able to conclude that it is doing a good job. And then further, is there evidence that the slope of the line is non-zero? That's this statistic and p-value right here. And so you'll notice this is a t-test with its p-value, and again this is very close to 0, so we do have evidence that the slope of the line is non-zero and there's a linear relationship between height and weight. So as always, if you have any questions about the code or you need any help, please feel free to let me know, and I hope that you have a great day.